A silent gale from the sun could power our spacecraft forever. This is the forgotten promise of solar wind propulsion, a revolutionary idea that once captivated scientists before it vanished from our blueprints. By the end of this journey, you will understand how this overlooked concept could completely reshape humanity's future in space, turning our star's breath into an endless engine. We will uncover why such a brilliant idea was abandoned for decades and explore the startling modern breakthroughs that might finally bring it to life. What does it truly mean to sail the cosmos not with fire but with the wind? The idea was born in a time when powered flight itself was still a miracle. While the world marveled at airplanes, a visionary astronomer named Friedrich Zander was already dreaming of a different kind of voyage. In the 1920s, he proposed a spacecraft that needed no fuel at all. His radical idea was to use the gentle, constant push of sunlight itself for propulsion. He imagined vast, mirrored sails catching the photons streaming from our star, turning light into motion. It was the first clear blueprint for what we now call a solar sail, a concept so elegant it seemed almost too simple to be real. But Zander was looking at only half of the picture. He saw the light but not the wind. That crucial missing piece would remain hidden for decades until another brilliant mind entered the scene. In the late 1950s, a young physicist named Eugene Parker was studying the sun's outer atmosphere. His calculations led him to a startling and, at the time, highly controversial conclusion. He proposed that the sun was not merely shining light, it was exhaling. A constant supersonic torrent of charged particles, a plasma of protons and electrons, was blowing outward in all directions. He called it the solar wind. For years, many senior scientists dismissed his theory as impossible. But in 1962, the Mariner 2 spacecraft confirmed it. Parker was right. The solar wind was real, so here we had two profound discoveries: Zander's vision of sailing on light and Parker's revelation of a ceaseless particle gale. The logical next step seems obvious to us now. Why not combine them? Why not design a sail that could catch not just light, but this newly discovered wind of charged particles? The potential was staggering. This wasn't just a gentle push from photons. This was the possibility of tapping into a far more powerful stream of matter flowing from the sun. It promised acceleration, maneuverability, and endurance that pure light sails could only dream of. Yet that next step was never taken. Not then. While these quiet visionaries sketched out a future of free, abundant energy in space, the world became captivated by a much louder, more visceral technology. The space race had begun. The immediate, thunderous success of chemical rockets with their fiery plumes and raw power captured the global imagination. They were tangible, they worked, and they could launch missions within political timelines. The subtle, patient promise of sailing on an invisible wind seemed abstract, slow, and uncertain by comparison. The solar wind concept was filed away, becoming a footnote in textbooks, a beautiful theory overshadowed by the roaring engines of the Apollo era. It would take a new generation, facing entirely different challenges, to dust off those old calculations and see them for what they truly were, a forgotten key to the stars. The roar of rockets had drowned out a quieter, more subtle truth about space. To understand the forgotten promise, we must first untangle two cosmic forces often mistaken for one another. Think of it like this: a traditional solar sail is a vast mirror-like sheet, perhaps miles across, deployed in the vacuum. It works by catching sunlight, but not in the way you might think. It isn't warmed by the light, it's physically pushed by it. Each photon of light, though it has no mass, carries a tiny amount of momentum. When billions upon billions of these photons bounce off the reflective sail, they impart that momentum, giving the spacecraft a gentle, continuous shove. It's an elegant dance with pure energy, a push from the sun's radiance. Now meet the solar wind. This is something entirely different. The sun isn't just a source of light, it's an active, boiling sphere of plasma. From its superheated outer atmosphere, the corona, it constantly blasts out a torrent of actual matter. This isn't light, it's a fast-moving soup of charged particles, primarily protons and electrons, streaming past Earth and out to the edges of the solar system. It carries both mass and immense kinetic energy, a genuine wind made of star stuff. So while a solar sail surfs on waves of light, a true solar wind propulsion system would need to catch this gale of charged particles. That fundamental difference changes everything. Harnessing a stream of matter with its own magnetic fields and complex behavior presents a far more intricate puzzle than simply reflecting light. It's the difference between flying a kite in a breeze and trying to capture that breeze in a bottle to power an engine. This distinction is the key that unlocks the unique and long overlooked potential of turning the sun's exhale into our throttle. This is where the forgotten concept transforms from a dream into a plausible machine. To catch a wind made of charged particles, you cannot use a cloth sail. You need something far more ethereal, yet incredibly powerful. You need a magnetic net. The leading theoretical model for this is called a magnetic sail, or mag sail for short. Its core idea is breathtakingly elegant. Instead of deploying a vast, fragile sheet of physical material, a spacecraft would unfurl a gigantic loop of superconducting wire. This isn't a sail in the traditional sense, it's an invisible force field generator. When an electrical current runs through this superconducting loop, it creates an immense magnetic field, a protective magnetic bubble that can stretch for hundreds of kilometers around the spacecraft. Think of it not as a canvas catching the wind, but as a powerful, invisible shield pushing against the flow. Now, remember what the solar wind is, a stream of charged particles like protons and electrons. These particles carry an electric charge, and charged particles are deflected by magnetic fields. So as this supersonic plasma gale blows past, it slams into the spacecraft's magnetic bubble. The particles are pushed away, and in doing so, they transfer their momentum to the magnetic field, which in turn pulls the spacecraft along. It's a gentle, continuous push, created by simply holding up a magnetic hand against the stellar breeze. The profound beauty of this system lies in its economy of motion. Once the superconducting coil is energized, it requires only a small trickle of electrical power to maintain its magnetic field, power that could be harvested directly from the sun with solar panels. The spacecraft expends no fuel to create its thrust. It is, in the purest sense, a wind-powered vessel for the cosmos, riding a current that has flowed for billions of years. But to move from elegant theory to a working starship, we must confront the immense scale of the challenge. Creating a magnetic bubble hundreds of kilometers wide is an engineering feat of staggering proportions. But that magnetic hand must be impossibly large. The solar wind is not a howling gale you feel on your face. It is an astonishingly thin haze. At Earth's orbit, there are only a handful of these charged particles in a space the size of a sugar cube. To catch enough of this ethereal breeze to move a spacecraft, your magnetic net must be cast wide, phenomenally wide. We are not talking about a structure the size of a football field. We are talking about a magnetic bubble that could comfortably envelop a small country. The theoretical designs call for superconducting coils forming loops tens, even hundreds, of kilometers in diameter. Picture the entire island of Manhattan or a city like Boston, outlined not in steel and glass, but in a fragile loop of wire floating in the void. This is the first, and perhaps most visceral, engineering nightmare. How do you manufacture a single, flawless coil of superconducting material that long? How do you compact it into a rocket fairing, launch it without damage, and then unfurl it in zero gravity with perfect precision. The forces involved are subtle but immense, and a single kink or break in that loop could collapse the entire magnetic field, rendering the sail useless. Then comes the environment. Space is not empty, it is filled with hazards. Micrometeoroids, smaller than a grain of sand but traveling at astronomical speeds, could sever the coil. Intense radiation can degrade materials over time. The spacecraft must also manage the tremendous electrical currents needed to generate the field, all while keeping the superconducting wire at temperatures near absolute zero. And this leads to the most delicate problem of all: control. How do you steer a vessel pushed by a bubble hundreds of kilometers wide? Tilting a magnetic field of that scale is not like turning a rudder, it is like trying to pivot a weather system. Small adjustments could require massive amounts of energy, potentially negating the efficiency that makes the concept so attractive. For decades, these were not just challenges, they were showstoppers. They confined the magnetic sail to the pages of speculative physics, a beautiful solution waiting for a problem we did not yet have the tools to solve. But technology never stands still, and sometimes the key to an old lock is forged in an entirely new workshop. The answer to these impossible engineering problems might not be a bigger coil, but no coil at all. What if the magnetic sail could build itself? This is the radical promise of the plasma magnet, a concept that turns the entire challenge on its head. Instead of launching hundreds of kilometers of fragile superconducting wire, a spacecraft would carry only a compact, lightweight antenna and a small tank of inert gas like xenon. Here is how this alchemy works. Once in space, the spacecraft releases a cloud of this gas and uses its antenna to inject energy into it, stripping electrons from the atoms and turning it into a glowing, magnetized plasma, a fourth state of matter. But this is not just any plasma cloud. By carefully controlling the rotation of this charged soup with magnetic fields, engineers can induce a powerful electrical current to flow within the plasma itself. This flowing current, in turn, generates a robust magnetic field, creating a self-reinforcing loop. The plasma essentially becomes a living, breathing coil of wire, one that can inflate to an enormous size without any physical structure to limit it. Think of it like blowing a soap bubble. You start with a tiny film on a small ring, but with a gentle breath you can expand it into a large, shimmering sphere. The plasma magnet works on a similar principle, using energy and rotation to inflate a magnetic bubble from a seed of ionized gas. The implications are transformative. The launch mass plummets from potentially thousands of tons of superconducting cable to a system that could fit on a modest satellite bus. The terrifying mechanical complexity of deploying a continent-sized loop vanishes, replaced by the elegant physics of controlling a cloud. The system becomes inherently more robust, as a plasma can heal around small perturbations, unlike a solid wire that can snap. Most importantly, it brings a once fantastical idea within the realm of a near-term demonstration. We are not talking about a century from now, but about a mission that could be designed and launched in the coming decades, a practical experiment to finally test if we can truly sail on the solar wind. Yet, mastering this ethereal engine requires us to solve a puzzle of a different kind, one written in the invisible language of magnetic fields and turbulent plasma. This gentle push presents a profound trade-off for any mission planner. The force generated by a magnetic sail, even hundreds of kilometers wide, is whisper-thin. Near Earth, its acceleration would be measured in millimeters per second each day. A chemical rocket could outrun it in a heartbeat, leaving the sail seemingly motionless in its fiery wake. This is the core dilemma of patience versus power. You are trading the explosive, immediate thrust of a rocket for a push so faint it feels at first like standing still. But in the frictionless ocean of space, a whisper, if sustained forever, becomes a roar. This is where the unique physics of the solar wind itself enters the equation, adding a layer of complexity. The strength of this stellar breeze is not constant. It fades dramatically as you journey outward. The force it can provide diminishes with the square of your distance from the sun. Double your distance, and the push you feel becomes only a quarter as strong. This means a solar wind vessel would be strongest in the inner solar system, yet its most epic journeys are to the places where that wind grows faint, the outer planets and beyond. So why would anyone choose such a delicate engine? The answer lies not in the starting line, but in the finish. A conventional rocket burns all its fuel in a spectacular, brief explosion of speed, then coasts silently for years. Its journey is a sprint followed by a very long glide. A solar wind ship never stops pushing. Its acceleration is continuous, day after day, month after month, year after year. While its initial pace is glacial, that speed compounds. Over a decade, a push of mere millimeters per second can build into a velocity that rivals our fastest chemical rockets, all without consuming a single drop of fuel. For missions whose goal is not a quick sprint to Mars, but a generational voyage to the Kuiper Belt, the Oort Cloud, or even on an interstellar precursor mission, this math becomes compelling. It is the ultimate tortoise and hare scenario. The rocket is the hare blazing ahead only to exhaust itself. The magnetic sail is the tortoise plodding inexorably forward, never tiring, and ultimately reaching destinations the hare could never dream of touching. The choice, then, is not about raw power, but about time and ambition. It asks us to design missions not for our political cycles, but for the steady, patient rhythm of the cosmos itself. Yet this patient engine reveals its greatest potential not within our solar system, but far beyond its borders. The true destination for a vessel that never stops pushing is the void between the stars. Out there, the solar wind itself fades away, merging into a far more tenuous sea, the interstellar medium. This is not empty space, it is filled with an incredibly diffuse gas, primarily individual atoms of hydrogen. There is almost nothing there, but for a spacecraft built on the principles of the magnetic sail, that almost nothing could become its fuel. This transforms our concept into something even more profound, an interstellar ramjet. Picture a vessel already traveling at a breathtaking fraction of light speed, perhaps 20 or 30%, stretched before it is a magnetic funnel, not just a bubble, hundreds or thousands of kilometers wide. As it hurtles through the galaxy, this magnetic net would sweep up those sparse hydrogen atoms from the interstellar medium. The ram effect of its own immense velocity would compress this collected material, which could then, in theory, be funneled into a fusion reactor at the ship's core. The reactor would fuse the hydrogen, providing thrust to both maintain speed and potentially accelerate further, all while gathering its own fuel from the space ahead of it. It is the ultimate expression of a self-sufficient voyage, a ship that drinks from the galaxy itself to power its journey. Of course, the challenges here are monumental, bordering on the realm of pure physics. The densities are so low that the magnetic scoop must be astronomically large. The engineering of a contained fusion reactor that can process this incoming stream is far beyond our current capabilities. And reaching those initial incredible speeds would itself require a civilization-scale effort. This remains a concept for the distant future, a blueprint for generations we may never meet. But its significance for us today is not in its immediate practicality. It is in the roadmap it provides. It tells us that the path to the stars may not be carved by building bigger chemical rockets. It may be paved by learning to speak the language of plasma and magnetic fields right here in our own celestial neighborhood. Mastering the solar wind with a magnetic sail or a plasma magnet is not just a clever way to explore the outer solar system. It is the foundational lesson, the first chapter in a much longer manual on how to navigate the cosmos without carrying everything with you. It teaches us to move with the galaxy, not just through it. So the real question becomes not which is better, but which is right for the journey. To see the solar wind sail's place, we must compare it to the current master of efficient spaceflight, the electric ion thruster. Think of an ion engine as a hyper-efficient but very thirsty marathon runner. It works by taking a small amount of onboard propellant, like xenon gas, and using solar power to strip electrons away, creating a plasma. This plasma is then accelerated out the back by powerful electric fields at speeds tens of times higher than chemical rocket exhaust. The result is a thrust so gentle you could barely feel it on your palm, but an efficiency or specific impulse that is extraordinarily high. It can run for years on a tank of gas the size of a large backpack, making it the perfect engine for nudging satellites into precise orbits or slowly spiraling probes out to asteroids. But it has one fundamental limit: its tank. Once the xenon is gone, the engine falls silent. Its total capability, its delta V, is strictly capped by the mass of propellant it launched with. Now place the solar wind sail beside it. This is a different kind of traveler altogether. It carries no propellant to expel. Its thrust comes from an external, cosmic resource, the sun's own particle wind. This means its potential delta V is not limited by a tank, but by time and the durability of its systems. In theory, it can push forever, or at least for as long as the sun shines and its magnetic bubble holds. This offers a truly unlimited change in velocity over the lifespan of a mission, a concept that makes mission planners dream of voyages lasting decades or even centuries. But this incredible endurance comes at a steep price: thrust. The push from the solar wind, especially with near-term technology, is far, far weaker than even the faint whisper of an ion engine. An ion thruster might produce a push comparable to the weight of a single sheet of paper resting on your hand. An early solar wind sail's thrust might be like the weight of a single grain of sand. This defines their domains. The ion engine is the master of missions requiring precision and moderate speed within the inner solar system, where its high efficiency with limited fuel shines. The solar wind sail is the patient pioneer for ultra-long duration missions to the outer solar system and beyond, where its unlimited endurance outweighs its initial slowness. The most compelling future, however, may not be a choice between them, but a marriage. Imagine a hybrid spacecraft, a vessel of both patience and precision. It could use a high-efficiency ion engine powered by large solar arrays to perform the critical, energy-intensive maneuvers, breaking away from Earth's orbit, making course corrections, or entering orbit around a distant world. Then, for the long cruise between planets, across the vast emptiness where time is abundant but fuel is precious, it would deploy its magnetic sail. The ion engine goes quiet, and the spacecraft begins its silent, fuel-free glide on the solar wind, accumulating speed year after year without spending a single drop of its precious xenon. This hybrid approach optimizes the unique strengths of both, using the ion engine for the sprints and the solar sail for the marathon. It turns the weakness of low thrust into a strategic advantage, allowing us to design missions of unprecedented scope and duration, missions that are not just about reaching a destination, but about sustainably exploring the frontiers that lie beyond. But this future was not always clear, especially at the dawn of the space age. When humanity first reached beyond the atmosphere, the choice of engine was never really a choice at all. The thunderous, visceral power of chemical rockets was the only tool that could do the job. To understand why the subtle promise of the solar wind was shelved, we must step back into that era of fire and urgency. The political landscape of the Cold War created a race defined by dramatic, visible achievements. The goal was not patient, efficient exploration. It was to plant a flag, to make a statement, and to do it first. Every mission was a high-stakes sprint, and in a sprint you do not start with a gentle, steady acceleration. You explode off the line. Chemical rockets delivered that explosive power. Their immense thrust, measured in millions of pounds, was the only force capable of wresting a spacecraft free from Earth's deep gravity well. They turned the theoretically impossible into a tangible, roaring reality within a single generation. The subtle nudge of a magnetic sail, which might take years to reach a meaningful speed, was utterly useless for the task of getting to the moon in a matter of days. The technology itself was a fantasy. The materials science for creating large-scale superconducting coils that could survive launch and operate in space did not exist. The computing power needed to model and control complex plasma interactions was in its infancy. They were ideas sketched on chalkboards, while the rockets were steel and flame on the launch pad. Furthermore, the early targets of space exploration were all close to home, in what we call the inner solar system. To reach the moon, Venus, or Mars with a chemical rocket was a voyage of months, not decades. For these shorter sprints, the raw speed of a high-thrust system was simply more advantageous than the ultra-high efficiency of a slow sail. The solar wind concept was a solution in search of a problem, a beautiful engine designed for a marathon in an age obsessed with the 100-meter dash. Its benefits, like unlimited range and zero fuel consumption, were luxuries for a calmer, more patient era of exploration, an era concerned with sustainable presence rather than symbolic firsts. We are now standing at the threshold of that very era. The political sprints have given way to a new imperative to stay, to build, and to journey farther than ever before. And for that new chapter, we are finally rediscovering the forgotten engines of patience. The forgotten engine now finds itself waiting in a new workshop, one stocked with tools its original designers could scarcely dream of. The revival of the solar wind sail is not being driven by a single breakthrough, but by a quiet convergence of technologies, each solving a piece of that once impossible puzzle. First, consider the very fabric of the sail itself. The dream of a massive superconducting coil no longer requires a miracle, just the steady march of materials science. The development of high-temperature superconductors, materials that can carry immense electrical currents with zero resistance at temperatures far warmer than absolute zero, changes everything. While still requiring sophisticated cooling, these advanced ceramics or compounds could enable powerful, compact magnetic coils that are far more practical to launch and maintain in the harsh environment of space. They bring the scale of the needed magnetic field down from the realm of science fiction to the edge of engineering reality. Simultaneously, our entire approach to building for space has transformed. Modern composites and metamaterials allow us to create structures that are astonishingly light yet incredibly strong. The gossamer frameworks needed to support antennae or deploy mechanisms can now be manufactured with a precision and resilience that would have seemed like magic 50 years ago. This reduces the launch mass dramatically, making the entire proposition more economical. But the most profound enabler may be the one that operates not in hardware but in code. The dynamic, chaotic behavior of a plasma cloud or a magnetic bubble interacting with the fluctuating solar wind is a control problem of nightmarish complexity. It is a system with millions of variables changing in real time, where a minor instability could collapse the thrust or send the spacecraft tumbling. This is where artificial intelligence becomes the indispensable captain of the vessel. An autonomous AI system, trained on vast simulations and equipped with a suite of sensors, could continuously monitor the state of the sail and the incoming solar wind. It would make millisecond adjustments to the electrical currents, the plasma injection rate, or the orientation of magnetic fields, constantly optimizing for stability and maximum thrust. It would navigate the solar wind storms and calms, the way an ancient sailor trimmed the sails to catch every whisper of a breeze. For a mission lasting decades, this is not a luxury, it is a necessity. Human controllers back on Earth, with signals taking hours to reach the outer solar system, cannot pilot this ship. it must sail itself, guided by an intelligence that learns and adapts throughout its epic journey. This technological trinity, advanced materials, lightweight structures, and autonomous AI, is what finally pulls the magnetic sail from the chalkboard and places it onto the drawing board. We are no longer asking if it is possible in theory, we are beginning to ask how we will build it. This quiet workshop is not filled with steel and wire, but with light and code. Before any physical prototype could ever be built, the magnetic sail must first be proven in a universe of pure mathematics, in the digital laboratories of supercomputers. Here, the chaotic dance of charged particles and magnetic fields is tamed into lines of logic, allowing scientists to conduct experiments that would be impossible in the real world. They use a specialized branch of physics called Magnetohydrodynamics, or MHD for short. While that sounds intimidating, think of it as a way to simulate a fluid that is also a magnet, which is exactly what the solar wind is, a magnetized plasma. These simulations are staggeringly complex, modeling billions of individual interactions to predict how a magnetic bubble hundreds of kilometers wide will deform, wobble, and push when struck by the sun's variable gale. Will the sail remain stable, or will it collapse under its own turbulence? How does it behave during a solar storm when the wind becomes a hurricane of particles? These are questions answered not with a hammer and wrench, but with algorithms and processing power. This virtual prototyping is where every parameter is tested. Scientists can adjust the size of the magnetic field with a keystroke, change the electrical current in the simulated coil, or alter the angle of the sail relative to the wind. They can watch in vivid color-coded visuals as their digital creation either surges forward efficiently or begins to spin uncontrollably, revealing fatal flaws long before a single gram of hardware is ever constructed. It turns the beautiful abstraction of theory into a detailed, stress-tested blueprint, identifying not just how it should work, but all the myriad ways it could fail. This phase transforms the concept from science fiction into a credible engineering challenge, one with defined problems that can be methodically solved. The path to the stars, it seems, is being paved first in silicon. This digital blueprint reveals a vessel built for journeys we have only just begun to imagine. Its unique profile of infinite endurance and gentle thrust carves out specific, profound niches in our future in space. One of its most immediate and practical roles would be that of a cosmic tugboat. Picture a future where infrastructure, like fuel depots or construction modules, needs to be moved from the bustling ports of low Earth orbit to more distant outposts near the Moon, or at the stable gravitational parking spots known as Lagrange points. A chemical rocket would be a costly, one-time delivery truck burning immense fuel for a single trip. A solar wind sail would be different. Once deployed, it could make this journey over and over again. It would latch onto a cargo container and begin its slow, patient push, taking months perhaps, but expending no propellant. After delivery, it simply turns around, sails back on the solar wind, and picks up the next load. It becomes a reusable, free freight service for building a sustainable economy beyond Earth, a silent workhorse of the high frontier. For pure scientific discovery, the sail offers a revolutionary perspective, turning the spacecraft itself into the instrument. Imagine not one, but a swarm of dozens of small, identical magnetic sails, released into space like a flock of mechanical dandelion seeds. Each one, with its ability to maneuver constantly without fuel, could station keep in a unique and otherwise impossible orbit. They could fan out, forming a vast, three-dimensional web around the sun. This would give heliophysicists their first true, stereo view of our star. They could study a solar storm from the front, the sides, and from behind simultaneously, tracking how these eruptions evolve as they travel. The sails would not just observe the solar wind, they would be riding it, feeling its every ripple and gust directly, transforming the entire fleet into a single, distributed sensor of unprecedented clarity. It would be like understanding a hurricane not from a single weather buoy, but from a cloud of drones flying within the storm itself. Yet, the solar wind sail's most epic calling lies in the deep, dark reaches beyond the asteroid belt. Our current probes to the outer planets are one-shot marvels of precise timing and gravity assists. They slingshot past Jupiter for a boost to Saturn, but rarely can they afford to slow down to orbit multiple moons or change course dramatically once there. Their propellant budget is the ultimate limit. Now envision a different kind of mission, a grand tour on the stellar breeze. A solar wind sail, after a patient acceleration spiral outward from the Sun, could arrive at Jupiter not as a speeding bullet, but as a vessel under full control. It could use its constant, gentle thrust to break into orbit around Jupiter, then spend years touring its icy moons, Europa, Ganymede, Callisto, using subtle pushes to hop from one to the next. After its survey is complete, it could then spiral back out, catching the solar wind anew to set sail for Saturn and repeat the process there. This is not a fleeting flyby, it is a residency. It offers the kind of persistent, multi-target exploration that could truly unravel the mysteries of ocean worlds and ring systems, a mission profile of patience and depth that our current propulsion simply cannot provide. It asks us to trade the brief, spectacular encounter for a long, intimate conversation with the distant giants of our solar family. The ultimate destination for a vessel that rides the sun's breath is the place where that breath finally fades into silence. This is the Heliopause, the invisible frontier where the solar wind's pressure can no longer push back against the gentle pressure of the galaxy. It is the true outer edge of our star's influence, a boundary we have only ever glimpsed twice with the Voyager probes as they slipped quietly across. A dedicated mission to this distant frontier is not just a scientific goal, it is a compelling flagship concept that perfectly matches the unique profile of a solar wind sail. Imagine a probe designed from the outset to do one thing, to sail directly for that boundary, powered by the very force it exists to study. Its elegance is profound. Unlike a conventional spacecraft that must carefully hoard its finite propellant for decades, a magnetic sail would use the solar wind itself for its primary propulsion. It would begin its journey in the inner solar system, where the wind is strongest, and accelerate steadily outward, building speed year after year. This constant, fuel-free push means it could potentially reach the heliopause faster than a probe relying on chemical rockets and gravity assists alone, shaving precious years off a voyage that already spans more than a decade. But speed is only part of the advantage. The real scientific treasure lies in what the sail frees the mission from carrying. Without the need for massive tanks of reaction mass, the spacecraft's mass budget is transformed. That saved weight can be dedicated entirely to power and instruments. Larger solar arrays could provide abundant electricity far into the outer solar system, and that power could feed a sophisticated suite of sensors, particle detectors, and magnetometers designed to map the heliopause in exquisite detail. This probe would not be a passive traveler like Voyager, coasting silently after its initial push. It would be an active vessel under continuous thrust, able to make subtle course corrections all the way to the boundary, ensuring an optimal approach angle. And upon arrival, with its instruments fully powered and its systems designed for the long haul, it could do something unprecedented. It could linger. It could station keep near this cosmic shoreline, measuring the turbulent interaction between our sun's bubble and the interstellar medium, studying it not as a moment in time, but as a dynamic, ever-changing region. This mission would be more than a journey. It would be a permanent sentinel at the edge of our solar home, a testament to the idea that the best way to explore a river is to build a boat that flows with its current. This stellar breeze is not a gentle, steady zephyr. It is a temperamental gale capable of erupting into sudden, violent storms, The most dramatic of these are coronal mass ejections, vast bubbles of magnetized plasma that the sun can blast into space at millions of kilometers per hour. To a conventional satellite, these events are a radiation hazard to be weathered, but to a magnetic sail, a coronal mass ejection is something entirely different. It is a powerful, unpredictable gust that could fill its invisible sails. The difference between a hazard and an opportunity lies entirely in navigation. Future solar sailors would not simply set a course and drift. They would become master meteorologists of interplanetary space, constantly monitoring forecasts from a network of solar observatories. Their guidance computers would integrate real-time data on solar activity, predicting the arrival, strength, and magnetic orientation of these plasma storms. With that knowledge, the spacecraft could perform a delicate dance. In anticipation of a strong gust, it might reorient its magnetic bubble, turning to catch the full force of the ejection, riding the wave for a tremendous, temporary boost in acceleration. Conversely, if a storm was too severe, threatening to overwhelm and destabilize the sail, it could turn edge-on, minimizing its profile to weather the blast safely. This transforms space weather from a passive threat into an active navigational tool. The vessel's path becomes a dynamic, calculated interaction with the sun's moods, a continuous optimization between safety and speed. It demands a profound fusion of disciplines where the spacecraft's guidance system speaks the language of heliophysics, interpreting the sun's fury not as noise but as a shifting map of currents and tailwinds. To sail on the solar wind is to learn to read the sky of a star and to have the wisdom to know when to trim your sails and when to run before the storm. The true cost of spaceflight is not measured in rocket fuel, but in the sheer weight of everything we must lift out of Earth's gravity well. Every gram launched into orbit carries an immense price tag, a figure that has shaped the entire economics of exploration. This is where the solar wind sail shifts from a scientific curiosity to a potential economic revolution. Its most compelling business case is not in what it adds, but in what it removes. By eliminating the need to launch thousands of kilograms of propellant, it fundamentally rewrites the ledger for any long-duration mission. Think about a conventional deep space probe. A significant portion of its launch mass, sometimes a third or more, is just the fuel it will later burn to maneuver and slow down at its destination. You are paying a fortune to launch a tank of gas that you will only use years later. A magnetic sail replaces that entire tank with a system that harvests its thrust from the environment. The immediate effect is a dramatic increase in payload capacity. All the mass, volume, and budget once reserved for propellant can now be dedicated to more powerful instruments, more robust communication systems, or simply a larger, more capable spacecraft bus. This means more science per dollar, a clearer signal from the edge of the solar system, and missions that are inherently more resilient because they are not constrained by a finite, irreplaceable resource. The economic ripple effects extend far beyond single scientific probes. Consider the emerging economy of cislunar space, the region between Earth and the Moon. As we look to build permanent outposts, fuel depots, and space stations at gravitational waypoints like Lagrange points, we face a massive logistics challenge. How do we move construction modules, supplies, and fuel tanks between these orbital ports? Using chemical rockets for every delivery run is like shipping packages across an ocean using disposable speedboats, a spectacularly wasteful proposition. A fleet of reusable solar wind tugs changes this equation entirely. Once deployed, these tugs could operate for decades, shuttling cargo on slow, steady, but completely fuel-free trajectories. They turn the high frontier from a destination reachable only by expensive, one-way tickets into a networked space with sustainable, scheduled freight lines. The upfront cost of developing the tug is amortized over countless missions, driving down the cost of building anything in space. This economic model could eventually open the door for private enterprise to participate in deep space in a way that is currently unimaginable. Today, missions beyond the moon are almost exclusively government endeavors due to their staggering cost and risk. But if a company could launch a satellite bus equipped with a solar wind sail, knowing its propulsion lifetime is effectively unlimited and its operational costs after deployment are minimal, new business models emerge. They could offer persistent monitoring services for asteroid mining ventures, provide communications relays for distant robotic outposts, or even deploy constellations for interstellar weather forecasting. The sail transforms a spacecraft from a consumable product with a fixed lifespan into a capital asset, a piece of infrastructure that can generate value for decades. It invites a shift in thinking from mission cost to lifetime value, paving the way for a truly self-sustaining economic sphere beyond Earth. The engine of this new economy would be the oldest power source we know, the endless breath of our sun. This vision of a sustainable space economy rests on a quiet ethical imperative. As our presence beyond Earth grows from brief visits to permanent settlement, the technologies we choose will define our legacy, not just for our own species, but for the pristine environments we are entering. Every chemical rocket launch, while a necessary tool for now, leaves a tangible mark, injecting exhaust into the upper atmosphere and contributing to a growing cloud of orbital debris from spent stages. Even the elegant ion engine, for all its efficiency, is ultimately a closed system that consumes a finite resource it carried from home. Its propellant tank, once emptied, marks the end of its useful life, adding another silent artifact to the celestial junkyard. The solar wind sail proposes a different relationship with space altogether. After the energy required for its launch and deployment, its propulsion is harvested, not taken. It creates no exhaust plume, sheds no propellant, and leaves no chemical signature in the void. Its engine is the sun's own natural output, a renewable stream of energy that has flowed for billions of years and will continue long after our spacecraft has completed its journey. This makes it perhaps the first truly clean and renewable method of transportation designed for the space environment. The implication is profound. It allows us to imagine a future where moving between worlds does not inherently pollute them, where a spacecraft can pass through the delicate plumes of an icy moon or the tenuous atmosphere of a dwarf planet without the risk of biological or chemical contamination from its own thrust. This aligns with a growing philosophy of planetary stewardship, the idea that as we expand into the solar system, we have a responsibility to preserve its scientific integrity and natural state. Choosing such a technology is not merely an engineering decision. It is a commitment to a sustainable, thoughtful expansion. It suggests a civilization that builds its highways from sunlight and magnetic fields, leaving the worlds it visits as undisturbed as possible, ready for the next generation of explorers, human or robotic, to find them not as used landscapes but as new frontiers. Yet this elegant, silent engine cannot sail alone. A magnetic sail may harvest its thrust from the void, but the vessel it propels is not a ghost ship. Its brain, its eyes, its voice all demand a steady, reliable flow of electricity. The instruments that map distant worlds, the communication lasers that whisper data back to Earth across billions of kilometers, and the very systems that generate and control the magnetic bubble or plasma cloud, they all require power. And this reveals a beautiful, synergistic partnership. For missions close to the sun, vast solar arrays can provide that energy, converting abundant sunlight into electricity. But as a ship sails farther out, past Mars and into the outer solar system, sunlight grows faint. Solar panels, no matter how large, become impractical, their output dwindling to a useless trickle in the perpetual twilight. Here, in the dark and the cold, the sail meets its perfect partner, a compact nuclear fission reactor. This is not the explosive power of fusion or the raw thrust of a nuclear thermal rocket. This is a steady, humming heart of atomic energy designed to do one thing: generate electricity for decades. Its fuel, a small amount of enriched uranium or plutonium, could provide kilowatts of power for 30, 40, even 50 years, completely independent of the sun's distance. Imagine the capability this union creates. A spacecraft with a nuclear reactor for electrical power and a magnetic sail for propulsion becomes something entirely new, a supremely capable interstellar precursor. It carries its own light and heat into the darkness, allowing its sensors to operate at full capacity even at the orbit of Neptune. It can maintain constant, high-bandwidth communication with Earth, streaming back high-definition video from the frontiers of the solar system. And it can do all of this while its propulsion system, the sail, continues its patient, fuel-free push year after year. This vessel is no longer constrained by the tyranny of the rocket equation or the fading power of sunlight. It is a creature built for the deep ocean of space, self-sufficient in thrust and energy, designed to operate where our current probes can only coast in silent austerity. It is the platform that could finally grant us a persistent, powerful presence in the realm of the ice giants and beyond, turning fleeting glimpses into enduring study. The silent, patient nature of this engine mirrors the path required to build it. Such a profound leap in capability demands a partnership on a global scale. The sheer magnitude of engineering a functional solar wind propulsion system, from the advanced materials to the intricate plasma controls, likely sits beyond the reach of any single nation's space budget or scientific portfolio. This is not a project for a lone pioneer, but a symphony for the entire orchestra of human ingenuity. It presents a perfect canvas for international collaboration on a scale we have only seen once before with the International Space Station. That orbiting laboratory proved that nations could set aside terrestrial differences to build something magnificent in the heavens, a shared outpost for discovery. A solar wind sail demonstrator mission could become the next chapter in that legacy, a unifying goal that lifts our collective gaze outward. Imagine the shared development of its core technologies. One nation's expertise in manufacturing next-generation superconducting wires could merge with another's leadership in plasma physics simulations. A third might contribute revolutionary lightweight deployable structures, while a fourth provides the advanced autonomous navigation software. By distributing both the immense financial costs and the deep technical challenges, the burden on any single participant becomes manageable, and the pace of progress accelerates for everyone. The result would be more than just a spacecraft. It would be a testament to what humanity can achieve when we channel our resources toward a peaceful, shared ambition. The first vessel to truly sail on the stellar wind would not carry the flag of a single country, but the shared emblem of a planet curious about its place in the cosmos. Its launch would be a landmark not for a government, but for the species, a signal that our greatest explorations are those we undertake together. The grandest voyages must begin with a single, quiet step. Before we can dream of sailing to the Heliopause, we must first prove the wind can be caught at all. This is the purpose of a Pathfinder, a small, focused mission whose only job is to answer one fundamental question. Can we generate measurable thrust from the solar wind? The ideal vessel for this first test would not be a majestic starship, but something humble and pragmatic, like a CubeSat or a small satellite. It could hitch a ride into space as a secondary payload on a routine rocket launch, dramatically lowering the cost and risk of this crucial experiment. On board would be a compact, engineered heart, a small-scale plasma magnet device. This would not be the vast, self-inflating bubble of future missions, but a minimal, tightly controlled apparatus designed to create a small, stable magnetic field and interact with the solar wind particles in a predictable way. The mission profile would be elegantly simple: Once deployed in a suitable orbit, perhaps one that periodically takes it through the higher energy streams of the solar wind, the satellite would activate its system. Its suite of sensitive instruments would then perform a meticulous dance of measurement. It would carefully monitor the magnetic field strength, the density and velocity of incoming particles, and most critically, any tiny, incremental changes in the spacecraft's own velocity and orientation. The goal is not to travel to another planet, but to perform a clean, unambiguous physics experiment in the vacuum of space. Success would be a dataset, a graph showing a clear, repeatable push that correlates perfectly with the activation of the plasma magnet and the flow of the solar wind. It would be the first direct evidence that this theoretical engine actually works. That single, quiet confirmation would be a thunderclap in the world of aerospace. It would transform the magnetic sail from a compelling simulation into a demonstrated technology, providing the critical proof of concept needed to secure serious funding and galvanize international interest for the next, more ambitious steps. It would validate decades of theoretical work with a simple, elegant whisper of data, turning a forgotten concept into the foundation of our next great journey. That first quiet step in space could echo for generations back on Earth. The most powerful legacy of a solar wind sail may not be the date it returns, but the story it tells. There is a deep, almost mythic resonance to the idea of sailing on a stellar breeze. While rockets thunder with the language of conquest and escape, the silent magnetic sail speaks of harmony and journey. It does not fight the cosmos, it converses with it. This narrative can capture the public imagination in a way that complex equations and engine specifications often cannot. It evokes the graceful silhouette of a clipper ship against the horizon, but translated onto the infinite black ocean of space. It is a vision of patience and elegance, of using the universe's own forces to explore it. For a young person seeing this concept for the first time, it reframes space travel. It is no longer just about the biggest explosion or the fastest rocket, but about intelligence, about reading the celestial weather and setting your course accordingly. It transforms the spacecraft from a projectile into a vessel, with all the romance and adventure that word implies. This is a story that can inspire not just future aerospace engineers, but also artists, writers, and philosophers. It invites everyone to see themselves not as mere spectators of space exploration, but as potential crew members on a much grander voyage, one built on sustainability and wonder. Communicating this vision is about more than public relations. It is about planting a seed for the kind of future we want to build. A future where our expansion into the solar system is guided by a principle of cleverness over brute force, and a profound respect for the stellar environment that makes our journey possible. But a magnetic field that spans a continent is not a private highway. It is a new kind of geography in the void, one that raises profound questions of responsibility. A spacecraft trailing an invisible bubble hundreds of kilometers wide fundamentally changes the rules of navigation. Today, space traffic control is a delicate ballet of calculating orbits to avoid physical collisions, often with margins of just a few kilometers. Now, introduce an object whose zone of influence is 100 times larger than itself. Its magnetic bubble, while diffuse, could potentially disrupt the sensitive electronics or guidance systems of a passing satellite, or distort the readings of a nearby space telescope studying faint magnetic fields from distant stars. The sail does not need to touch another object to affect it. This creates a novel category of right-of-way, where the mere presence of a magnetic sail could require other vessels to alter their course, not for fear of impact, but for fear of electromagnetic interference. It demands a new language for space traffic, one that includes magnetic exclusion zones and priority protocols for vessels under sail. Who has the right-of-way in such a scenario? Is it the smaller, more maneuverable satellite, or the larger, less agile sail whose course adjustments take days to enact? These are not just technical puzzles, they are foundational questions for the rule of law beyond our atmosphere. The development of the technology cannot race ahead of the frameworks needed to govern its use. We must establish international norms and safety standards now, while the first sails are still on the drawing board, to prevent conflicts and ensure the safety of all spacefaring nations. This is not about restricting innovation, but about channeling it responsibly, ensuring that this powerful tool for exploration does not inadvertently become a source of tension or hazard in the increasingly crowded skies above us. Ownership of the stars themselves remains a legal fiction, but the machines we use to sail upon them are another matter entirely. As magnetic sail technology transitions from research papers to engineering prototypes, a quiet but critical question emerges from the drafting tables and simulation labs. Who owns the ideas that will power this new kind of voyage? The journey into this frontier will be navigated not only by magnetic fields, but by complex intellectual property law. Can a private company secure a patent on a specific method for generating and stabilizing a plasma magnet? Could another entity own the exclusive rights to the most efficient superconducting coil configuration for deep space applications? These are not abstract debates, they are practical hurdles that will directly shape who builds the first sails and for what purpose. The incentive for private investment is clear. Developing these systems requires immense capital, and patents offer a period of exclusive commercial rights, a chance to recoup that investment and profit from a revolutionary technology. This protection can be the catalyst that turns a laboratory breakthrough into a flight-ready product. Yet, the history of space exploration offers a crucial lesson. The greatest leaps often come from a delicate balance between proprietary innovation and open scientific exchange. Consider the foundational technologies of rocketry and satellite communications. While specific implementations were patented, the underlying physics and much of the basic research flowed through academic journals and international conferences. This open exchange allowed scientists and engineers everywhere to build upon each other's discoveries, accelerating progress for all of humanity. The challenge for solar wind propulsion will be to strike that same balance. We must create a framework that rewards the risk-takers and engineers who turn theory into hardware, while ensuring that the core principles of harvesting energy from space remain part of our shared scientific heritage. The goal is to avoid a scenario where the very concept of sailing on the solar wind becomes locked behind a thicket of overlapping patents, stifling innovation and making it prohibitively expensive for academic or international scientific missions to participate. The ideal outcome is a constellation of protected, competing implementations, all built upon a foundation of openly understood physics. This way, the wind itself remains free for all to use, while the craftsmanship of the finest sails can rightfully belong to those who learn to build them. Every grand vision must withstand the scrutiny of a practical mind. For all its elegance, the concept of solar wind propulsion faces serious and well-founded criticisms from within the scientific community. The most immediate critique is one of sheer practicality. The technical hurdles remain monumental, from creating stable plasma clouds to deploying continent-scale magnetic fields without them tearing themselves apart in the turbulence of space. Even if built, these vast, invisible structures would be acutely vulnerable. A powerful solar storm, a coronal mass ejection, would not be a mere gust for such a sail, but a potentially catastrophic hurricane. The same magnetic forces that provide thrust could become twisted and unstable under such an assault, risking the integrity of the entire propulsion system. And then there is the inescapable physics of the thrust itself. Critics rightly emphasize that the push from the solar wind, especially in the outer solar system, is vanishingly small. Compared to the immediate, decisive acceleration of a chemical rocket or even the steady whisper of an ion engine, the magnetic sail's acceleration can feel inconsequential, a force best measured over decades, not days. Given these formidable challenges, a skeptic might ask a very reasonable question. Why pour limited resources into such a fragile, slow technology when we could refine what we already know works? Investing further in high-efficiency electric propulsion or developing robust nuclear thermal rockets seems a safer, more immediate bet for exploring Mars or the asteroid belt. These are not objections to be dismissed. They are essential engineering and economic realities that must be factored into any honest roadmap. The response from advocates is not to deny these hurdles, but to reframe the entire premise. The magnetic sail is not a replacement for every mission. It is not the tool for a sprint to the moon or a rapid crewed mission to Mars. Its value is unlocked only when we think in terms of centuries, not congressional budget cycles. The investment is not in a single engine, but in a fundamental capability, the ability to travel the solar system without carrying the fuel. This is a paradigm shift, akin to moving from disposable, single-use rockets to reusable, sustained infrastructure. The payoff is not a faster trip to Jupiter, but the permanent, sustainable presence of a scientific observatory there, or a reusable tug that can service space stations for 50 years. The research and development needed to overcome those technical hurdles in plasma control, advanced materials, and autonomous navigation would spin off innovations that benefit every other area of space technology. So the debate ultimately circles back to the kind of future we aim to build. Do we continue to craft exquisite, one-time fireworks that briefly illuminate the darkness? Or do we begin the patient work of weaving a sail, learning to move with the universe's own rhythms? The answer will define our legacy among the stars. Such a journey from blueprint to starway must be mapped not in wishes, but in tangible, phased milestones. A plausible timeline for this forgotten engine begins not with a grand launch, but in the quiet hum of laboratories on Earth. Throughout the next decade, the critical work will unfold on the ground. Physicists will run increasingly sophisticated plasma experiments within powerful magnetic chambers, simulating the chaotic interplay between a manufactured magnetic bubble and a stream of charged particles. Concurrently, the first subscale demonstrators, perhaps built on the compact frame of a CubeSat, will reach orbit. Their goal is not to travel anywhere, but to answer that single, fundamental question in the real environment of space, confirming that the physics translates from simulation to reality. This phase is all about proof of principle, gathering the data that turns a beautiful theory into a credible engineering discipline. Building on that foundation, the 2040s could herald a more ambitious step, a medium-scale technology validation mission. This would not be a humble CubeSat, but a dedicated spacecraft, perhaps the size of a small car, sent into interplanetary space between Earth and Mars. Its purpose is to graduate from proving the physics to testing the engineering. Can the plasma magnet maintain stability for months or years? How does it respond to real solar storms? Can we reliably control its orientation and extract predictable thrust? This mission would be the final exam before committing to a vessel of true exploration, ironing out the 1,000 tiny failures that precede any great success. With those lessons learned, the horizon of the 2050s or 2060s comes into view. This era could witness the launch of the first full-scale operational solar wind sail. Enabled by breakthroughs in materials, autonomous artificial intelligence, and compact power systems, this would be a vessel designed for a legacy. Its mission profile would be measured in decades, a patient, fuel-free voyage to the outer solar system. It might be the Heliopause Sentinel, the Jovian System Tourer, or the reusable deep space tug. This launch would mark the moment the concept sheds its experimental skin and becomes a practical tool, a new class of spacecraft joining our celestial fleet. Each phase, each decade of diligent work, builds the staircase from a forgotten concept on a chalkboard to a cornerstone of our interstellar ambition, proving that the most profound journeys begin with the patience to take the first quiet step. This journey began with a quiet question in an age of roaring engines. We have traced the solar wind from a dismissed theory to a tangible river of particles, and followed the dream of a magnetic sail from a physicist's sketch to a digital prototype in a supercomputer. The distance between a forgotten concept and a working starship is measured not in kilometers, but in decades of human curiosity and perseverance. It is a story that reminds us that our greatest tools are not always the loudest, but often the most patient. The rockets that took us to the moon were monuments to our will to escape. The sail that could take us to the Heliopause would be a testament to our wisdom to listen, to learn the rhythms of our star and move in harmony with them. This is the true paradigm shift from conquering space to conversing with it. The technical hurdles ahead are real, from stabilizing plasma to navigating with fields wider than continents. Yet, these are not walls, but simply the next set of equations waiting to be solved, the next generation of materials waiting to be forged. Each challenge overcome adds another stitch to the fabric of this cosmic sail. The potential reward makes the endeavor worthy of our finest minds. Unlimited propulsion unlocks missions of unimaginable duration and scope. Sustainable exploration means we can visit other worlds as guests, not as disruptors. A pathway to the stars becomes not a frantic leap, but a patient, generations-long voyage, powered by the same breath that gives our planet life. We stand at a unique crossroads in history. For the first time, the necessary technologies are converging, and the need for such a gentle engine is becoming clear. The next chapter will be written by those who choose to look past the traditional plume of fire and see the invisible gale rushing past our planet. It invites us to design not for the next political cycle, but for the next century, to build infrastructure that endures and explores on timescales that match the cosmos itself. The future of our journey into space may not be found solely in building more powerful rockets, but in learning to raise a sail. The wind has been blowing for billions of years, a silent, endless invitation. The question now is whether we are ready to set sail. If this vision of a future written in magnetic fields and stellar breezes excites you, we would love to hear your thoughts. Share them in the comments below and subscribe to join us as we continue exploring the next frontiers of technology, one idea at a time.